Morning, guys. Excuse me. First of all, let me apologize. The quiz yesterday was all messed up. Peter Quinn realized that I had gotten 2 5s in a row and only counted one of them. I thought I had made a mistake in counting. I thought I only had 7 rolls. I thought that the 2 5s were somehow counted twice, and so I goofed up. Peter got it right. So you ran the chaos game. I hope you ran it long enough to see a pattern. I hope you ran it on a computer simulation. I hope you found out that you got this thing which math calls the Sierpinski triangle. On my phone, it looks something like that. Let's draw it. Doesn't have to come from an equilateral triangle. It can come from any triangle. The chaos game first leads you to this triangle in the middle, formed by the mid-segment of the big triangle, and this triangle is empty. And then these triangles, formed by the mid-segments of mid-segments, are also empty. And then these are empty. And these are empty. Etc. As they say, forever, forever, forever. This thing is what they call a fractal. Fractals are pretty cool objects. They have a lot of strange properties. They're often the result of this sort of infinite process that we carried out in the chaos game. They're often the result of some sort of randomized process. It's actually pretty cool that this random process in the chaos game leads to such a beautiful pattern. I hope you saw it when you investigated on the internet. If you didn't, I'm sorry. That was your responsibility yesterday. Fractals give us some interesting things to study. The first place we're going to take the Sierpinski triangle is we're going to ask how much of this triangle is empty. That is to say, if we take this triangle inside and these triangles inside and these triangles inside, how much of the triangle do they add up to? Sort of what percent of the original triangle do they add up to? And I want to think of it this way. If the original triangle has area 1, then what about the smaller triangles? And I want to ask it in this way. Question number 1. How many of these size triangles are there? Question number 2. Relative to the original triangle, what is the area of the smaller triangle? So if the original triangle has area 1, then this triangle on the inside, which I guess is going to come out to be orange, has what area? And then I want to take this number, which we can see is 1, and this number, which we can see is 1/4, and multiply them together for a total empty area so far of 1 times 1/4 or 1/4. Next question. How many of these triangles are there? What's the area of each? And what's the total area? Well, it's pretty clear to see that we see 3 of those triangles. What's their area? Well, that orange triangle here is relative to this triangle, just like this one is to the original. So that this orange is 1/4 of this triangle, and this triangle is 1/4 of the entire thing. So this is 1/4 of 1/4. The area of each is 1/16 for a total of 3 times 1/16 equals 3/16. What's the pattern? Well, let's do one more and see. How many of these little triangles are there? We see 1, 2, 3, 4, 5, 6, 7, 8, 9 of those little triangles. And each one of them is 1/4 of 1/4 of 1/4. We originally took out 1/4, then we took out 3/16, then we took out 9/64. There's a pattern here. What's the pattern? Each one is arrived at by multiplying the previous one by something. Arrived at by multiplying the previous one by something. And it's the same thing every time. What's it the same? What is it? You tell me. What goes in there? What goes in here? Tell me this is a decimal. Tell me this is a decimal. And then I want to look at the pattern. And ask, what's the total amount that gets removed from the Sierpinski triangle? Figure that out. Talk to you tomorrow.